c plus v squared s equals v squared c minus grs, and isolate. And so now my formula for mu for this particular problem is the v squared times the cosine of theta minus gr sine of theta divided by gr cosine of theta plus v squared sine of theta. So we haven't made a careless error. It's a plugging judgment. So 30 squared times the cosine of 35 degrees minus 9.8 times 100 times the sine of 35 degrees divided by 9.8 times 100 cosine of 35 degrees plus 30 squared sine of 35 degrees. And someone is about to tell me what the answer is. What'd you get?
0.132.
132?
133.
133. Anyone else get the same thing? Or something different? The same thing? All right. Units? All right. So, the coefficient of friction is a minimum 0.133. The car is not going to slide, given the scenario here. Car's traveling about 62 miles per hour as it goes around this curve. So it doesn't require a whole lot because you're not that far off of the ideal angle. Questions up to here? All right, what is the maximum coefficient of static friction? We found the minimum. What's the maximum?
Would the angle be 42.56 instead of 35?
No, we'll keep the angle at 35 degrees. Hint, it's a conceptual question. Why one?
Sounds good.
Oh, I thought somebody, I heard a noise.
The point just before
still liking 1. Robert also sort of echoed 1, but I don't know if you like it as much as Kelly does.
I mean, I don't know how to gauge how much she likes it, but I'm confident with it.
You're confident with 1?
Yeah.
Okay. All right, remember that the coefficient is some indication of how hard it is or easy it is to slide. As long as I'm not below that, if it were frictionless, that car would definitely slide. So we increase that static friction, the static coefficient until we get to a minimum point of 0.133, so it's not gonna slide. And then we can keep increasing it forever. So I've seen very few coefficients of static friction bigger than 1. So in that respect, you might get away with an argument for 1. However, infinite. There is no maximum really. So, all right. We could change the problem. It's now just a matter of what you given and what do you need to find? Because I could have given you the static coefficient and then asked what is the maximum angle at which it won't slide. And I've done things like give this problem, you solve for mu sub s, and then in the next problem I say, suppose mu sub s is 0.133, what's the maximum angle on which it won't slide? So if you got that correct, then it'd be simple, it's just 35 degrees. However, if you got that wrong, then that next problem would be very tricky. All right, moving on. See if we can wrap up chapter 6 here. I think it's spelled right. 1 T, 2 L's?
Yeah.
All right. So that's a radius of Earth. And we'll let this be half the radius of the Earth. If the satellite is to maintain this orbit, how fast does the satellite need to travel? I am assuming that it is not going to run into anything that is in no air resistance, not hitting any space debris, et cetera, et cetera. So, what's the first thing we do? Absolutely. That has not changed. Still the same process. So what are all the forces acting on the satellite?
Gravity.
Sweet. Combine the two concepts. Gravity, huge topic, looking for just a small aspect of it.
Gravitational pull.
Pardon?
Gravitational pull.
Okay, I'll buy that. Or I was thinking force due to gravity or gravitational force also. The reason why weight, I was not really thinking weight is acceptable because it's not really close to the surface of the planet, so weight sort of loses meaning at that point. But we do have this gravitational pull acting towards the planet. Likewise, the planet's being pulled towards the satellite, but because the mass of the planet is so big compared to the satellite, I'm assuming, that it's not really a noticeable effect on the Earth.
Is that a C or a G?
That's an F subscript G for gravitational force. Because we are dealing with a much farther distance from the planet, weight is not acceptable, so we do need to go to the generalized symbol for gravitational force. Bless you. What is the direction of acceleration of the satellite?
Towards the grid.
Okay, so my acceleration is in that direction. So when I set up my coordinate system, as was gestured back there, I'm going to make that, I can make it I hat J hat, R hat, whatever I want to use it for, but it's a one-dimensional problem. I've only one force acting on the satellite. So I can get away with just a plus. Let's see, that's the coordinate axes decomposition. What do I need to break up? Okay. Equations of motion. Oh, yeah, okay, that's the number. And what is the equation of motion?
The gravitational force equals NA.
And it's centripetal acceleration. All right, substitution now. What's the formula for acceleration?
E squared over 4.
And the formula for gravitational force? Okay. If we know what the acceleration due to gravity is that far out, we could use mg, but we don't generally know the gravitational acceleration anywhere except near the surface of a planet. So we need another formula here. And this force due to gravity, well, I know that the farther something is away, the less force there is. So whatever that distance is, it's going to be the denominator, because the bigger it is, the smaller the force is. So r, this happens to be r squared. I can rationalize it, but mainly experimental. What else does the force of gravity depend upon?
The mass of the satellite.
Okay. And
G.
and g.
G.
Well, I don't think it's what you intended, but there is a capital G. There's one other piece missing. Because from Newton's third law, that the force between two objects is going to, the magnitude of the force between two objects is the same. So the force that the Earth pulls down on the satellite is the same magnitude of force that the satellite pulls up on the Earth. If I flipped the two objects in space, that force should not change. So this depends upon both masses.
Yeah.
So mass 1, mass 2 generally. Now, this is the equation that we'll use the most, and the direction, we'll just think through it, but there's a slightly more formal way of writing this, which I will do. It is a vector, so put the vector symbol there. It is always towards the center of the other object. So negative r, so this would be the force due to gravity on object 1 from object 2. And it's towards the center of 2. So this notation here is, this is the force on mass 1 from mass 2. Mass typically has only, oh, I didn't write that correctly. I just wrote incredibly sloppily. So this is a more formal writing of this force due to gravity. The negative R2 hat is purely directional. We've already thought through, we know the direction is going to be towards the center of the Earth, because Luis said so. But I'm making that the positive direction, so it's big G, mass of satellite, mass of Earth over r squared. R is the distance from center to center. That's R. Now, this mass right here, since I do have two masses involved, which mass is this?
The satellite.
It's the one that's undergoing centripetal acceleration. It is indeed mass of the satellite. If you'll notice, I now have a factor of mass of the satellite in both numerators. It will cancel out.
And the other one beside massive satellite on the G side is?
Mass of Earth. So I've now reduced this down to, I have big G times mass of Earth over R squared is equal to V squared over R. So this now becomes that. Couple comments here. This big G that was accidentally spoken earlier, this is known as the gravitational constant. There are three things that students will all call gravity, that some students will call gravity. One is the acceleration due to gravity, one is the force due to gravity, and one is the gravitational constant. Which is why I get picky, because they are three different things. They are all aspects of gravity, but they are all slightly differently used. The purpose of big G primarily is to make sure the units work out. Because force is in newtons, mass is in kilograms, R is in meters. That's just a unit vector, it has no units. So G is going to have units of Newton meters squared per kilogram squared. And the value, 6.67 times 10 to the negative 11 in SI units. Now there is a unit system. This is sort of a side note. There is a unit system in which big G is equal to 1. These are called naturalized units. In that same unit system, the speed of light is equal to 1. And that's something that theorists do because they don't have to deal with all the letters. We will not do that. We'll stick with the international standard. All right. Some textbooks, if you go back far enough especially, this was sometimes called the universal gravitational constant. However, it is subject to debate whether it is indeed universal. It's rather arrogant of us to call it universal because we are just in a small spot within a large galaxy within the universe. So we don't know whether this value is true in other galaxies, but it is true locally, at least. Locally, our solar system, it really seems to work. All right, so another side note before we continue down there. Because this is a gravitational force between two masses, what's the gravitational force between me and an average one of you? Well, we can figure that out. Force due to gravity, the magnitude of the force due to gravity, is equal to big G, 6.67, times 10 to the negative 11, Newton meter squared per kilogram squared, times my mass, which is about 100 kilograms, times your average mass, which is 62 kilograms. Divided by the distance squared. So let's see, let's just pick Peyton. That's about 5 meters. That's not good. Over 5 meters squared. Someone would be kind enough to do that calculation. Now, I will say that if you don't have your calculator here, please make sure you still know how to do this. And so many people not know how to use this times 10 to the negative 11. 5 times 10 to the negative 9th. No 8th. Nobody's got to tell me. Somebody. Tension's mounting. Excitement builds. Kelly, what do you have?
I have negative 2.5 times 10 to the.
Do you have a negative number?
Yeah, that sounds about right. I think I did it wrong.
Yeah, this, if you're just doing this, you should not be getting a negative number.
Okay. Is that negative 11?
That's a negative 11. That's the exponent.
Okay, maybe I didn't do that right.
1.65 times 10 to the negative 8.
All right, and units? What do we find?
Newtons?
Somebody just said it.
Was it Newtons?
It is indeed. We just found a force. So it's not an incredibly huge force there. There's still a gravitational force, but we don't have anything here where we could actually measure the amount of that force. This is incredibly high precision equipment that would measure something that small. Wake Forest, I know, has got some stuff that'll measure forces down at that level. They have something that, they have this device that will rip molecules apart and measure the force it takes to rip a molecule into. Atomic force microscope? That's not it, something like that. All right, so there's a gravitational force, but when we do the force diagrams, we leave this out because these are so tiny compared to the others. The people who care about this level of force are people who are actually who are doing gravitational experiments. Now, there was a group that was trying to